Um, last week we talked about eigenvalues, eigenvectors, and we're going to recap a little bit of that stuff today just because it's really important and it's worth seeing repeatedly. This transformation is going to be written with respect to the standard basis. Okay? So we don't know exactly what that means just yet. But it'll become a little more clear as we go. So every matrix, every linear transformation can be written in matrix form once you specify a basis that you want to use. Okay, so we've already seen that linear transformations on some level have nothing to do with matrices, right? In the sense that a linear transformation is just something that satisfies this property here. That it splits over sums and that you can factor out constants, right? So there's no matrices anywhere in that, right? It's just a transformation in which it splits over sums and you can factor out constants. And so the question becomes, if that's all a linear transformation is, where does this matrix business come from, right? And so given the linear transformation, once you choose a basis that you want to use to describe your space, that's the point at which you can start to introduce matrices to describe the linear transformation out. Okay? And so what we're doing here is we're just going to assume that we've chosen the standard basis 1, 0, and 0, 1. And we're describing that linear transformation as a matrix now, using those two vectors. Okay? And so you'll notice that this is clearly not a very pleasant transformation. And if we were to have this transformation operate on a random vector, something like something like 1, 0, then just doing this matrix multiplication, you'd end up with basically this column as your answer, 16, negative 7. And so just like last week, we can draw the geometry of what's going on here. We've got the input vectors is 1, 0. And the output is 16, negative 7. So something like way down here. 16, negative 7. And so the input vector, 1, 0, has basically been rotated by negative 23 degrees and stretched by a factor of 17.46. So this thing is 17.46 times as long as the original. Certainly isn't all that clear when it's written in this, using this basis, what the underlying geometry is. And so we discussed last week the idea that, eigenvalues and eigenvectors give you a really nice way of rewriting the transformation so where it's a lot more clear what's going on. So let's go and calculate the eigenvalues. On the left just says take lambda I minus your transformation. And so lambda I is just going to be identity with lambda instead of 1. And then minus A is going to be 1642 minus 7. Make it minus 19, thanks. And looks kind of terrible. This turns out to be the determinant of lambda minus 16, minus 42, 7, and lambda plus 19. Looks pretty terrible, but it turns out to factor kind of nicely. So this ends up giving you the polynomial lambda squared plus 3 lambda minus 10. Okay. And we set that equal to 0 and we solve, right? So in this case we see this factor as lambda plus 5, lambda minus 3, sorry, 2 rather. And so we get these two eigenvalues, minus 5 and positive 2. Okay. We're not going to go through both calculations, but let's go ahead and find an eigenvector associated to the eigenvalue 2, just to sort of recap that really critical procedure. We know that the definition of an eigenvector is that AV has to send you to a constant multiple of V, where in this case we're going to consider that eigenvalue 2, right? So we've got our matrix A, which is 16, 42, minus 7, minus 19. Our vector, we're going to write it as AB, and we want it to equal 2 times AB. All right, so I'm going to write this in linear system notation. This is 16A plus 42B equal to 2A, and minus 7A minus 19B equal to 2B. And then we can rewrite this in slightly different form. Let's put the A's on one side and the B's on the other. So equation 1 becomes where we get 14A equal to negative 42B. And equation 2 becomes what do we get? 7A equal to negative 21B. Okay. So these are the same equation, just like we saw last week. And all that we need is to just choose an A and a B that make this equation true, and that gives us our eigenvector, right? So in this case, let's go ahead and set A equal to 3 and B equal to negative 1. Actually, in the notes, I choose them differently. I choose A to be negative 3, so we'll be consistent with the notes. Choose A equal to negative 3, B equal to 1. And so we have this eigenvector then. Negative 3, 1. And, you know, I just wanted to go through that one more time because it's important enough to where it's worth seeing multiple times. And so, similar procedure. For lambda equal to negative 5 yields an eigenvector of, I guess we'll call this a V1, call this V2, yields an eigenvector of negative 2, 1. And so we've got ourselves an eigenbasis then for this vector space, right? And so what we're going to do is we've got this transformation. In which the geometry of the transformation is not real clear. And what we're going to do is, instead of using the standard basis, 1, 0, and 0, 1, let's instead rewrite everything in terms of eigenvectors first, okay? Okay. And so, as an example, let's go and consider this vector W, just given by -7, 1, where we're writing this in terms of the standard basis, right? Then what we're going to do is we're going to rewrite this in terms of the eigenbasis. Which we found to be -3, 1 and -2, 1. So we've got this set of basis vectors, and we want to generate -7, 1 as a sum of these things. So C1 times V1 and C2 times V2. And so, this ends up just being a simple matrix equation, right? This says, I wish I hadn't written it in this order. I'm going to switch the order around, okay? But all of this says, it says take -3, 1, sorry, -3, 1, and -2, 1 times this column C1, C2 equal to this vector written in the standard basis. -7, 1. These are also written in terms of the standard basis. This is the first eigenvector written with the standard basis. Second eigenvector written with the standard basis. Okay, so this is just a system of equations, and you just solve it using basic row reduction, which we'll skip because everyone's done about 1 million row reductions in their life, right?
Well, I'm going to.
Okay. We could make it one more if you guys really want. And so you row reduce, you find C1 equal to 5 and C2 equal to -4. Okay. And so what this gives us then is this is the coordinates of this vector -7, 1, but written in terms of the eigenbasis rather than the standard basis. have then is that negative 7, 1, in terms of the standard basis, is 5, negative 4, written in terms of the eigenbasis. So I'm just going to keep drawing these pictures. I'm not sure if you guys are already comfortable with this idea, and drawing this picture is going to be redundant, but I just think it's really important to draw this picture. We've got the standard basis, 1, 0, 0, 1, and we're looking at this vector w, which is at negative 7, 1, so way out here. And what the eigenvectors look like is we've got negative 3, 1, so there's our first eigenvector, and then negative 2, 1 is going to be this eigenvector. And so the coordinates with respect to this new basis are, we're going to take 5 copies of V1, so that would shoot it out. We're going to take 5 of those, and we're going to take negative 4 of this vector. And adding these two things together using the parallelogram law, we'd end up getting this vector here. And so this is these coordinates that give the eigenbasis coordinates, that the scalars that we need for the eigenbasis to represent that vector w in terms of that eigenbasis. Okay. And so up till now, we've basically just been talking about coordinates without really giving them a proper definition. It's something I should probably clean up in the notes. But the coordinates of a vector with respect to a given basis are the scalars needed to rewrite whatever vector you're looking at. So the coordinates for a vector are just the scalars needed to write that vector as a sum of the basis vectors that you're using. Okay? So that's it. That 5, negative 4, those are the scalars that you need to write this vector negative 7, 1 in the standard basis in terms of the eigenbasis. And so those are the coordinates with respect to the eigenbasis. Okay? Questions so far? So what we're going to do is we're going to start rewriting this transformation, the one with the messy numbers, and we're going to do it using the eigenbasis rather than the the standard basis. But what we're going to do is we're going to do it in sort of a piecemeal fashion where we can construct it step by step. And so we've got this transformation. -7, -19. So given this transformation, and I guess I'll write here that it's written in terms of the standard basis. How can we make this thing operate on vectors that are written in terms of the eigenbasis? Right, because as of right now, if you want to plug something into this matrix, it has to be written in terms of the standard basis for you to do that. So how can we get this thing operate on vectors written in terms of the eigenbasis? And the answer to that is actually pretty simple. All we do is we're just going to take vectors that are written in terms of the eigenbasis, and we'll just transform them back to the standard basis first. That's all there is to it. You've got a vector written in terms of your eigenbasis. That doesn't match with this coordinate description, so just send it back to the standard basis and then it matches, right? And so what we'll do is let's create a matrix that does this, okay? Let's just take the eigenvectors that we've got, the eigenvectors v1, v2, and let's express those things using the standard basis. Just turn them on their side and stack them into a matrix, okay? So, in this case, remember that in terms of the standard basis, the first eigenvector was -3, 1. The second eigenvector was -2, 1. And so this matrix here is the tool that we're going to use to transform vectors written with the eigenbasis in terms of the standard basis, okay? Let's consider this vector 1, 0, written in terms of the eigenbasis. Then let's go ahead and hit this thing with that matrix there. So -3, -2, 1, 1, and what do we get? Well, matrix multiplication just gives you this column, -3, 1, and so this tells us something very simple. It says the first eigenvector written in terms of the eigenbasis is just going to be 1, 0, because you're just taking one copy of the first eigenvector. If you want to transform that back to the standard basis, what do you get? Well, written in terms of the standard basis, the first eigenvector was just -3, 1. So this matrix then transforms this basis eigenvector into its coordinate description in terms of the standard basis, okay? And the same thing holds with 0, this is the second eigenvector written in terms of the coordinates for the eigen, using the eigen basis coordinate description. And so just multiplying that out tells you that the second eigenvector written in terms of the standard coordinates are -2, 1. Okay. And so what we can do is we've got this vector W, which when written in terms of the eigenspace, in terms of the eigenbasis, that vector W was 5, -4. Is that right? You guys remember? Yeah, 5, -4. And so if we want to see what this is written in terms of the standard basis, all we do,
Multiply by that.
yeah, exactly, we've got our matrix here. Multiply by this guy that's written in terms of the eigenbasis. And lo and behold, what do we get? -15 plus 8 is 7. And 5 minus 4 is 1. Sorry, -7. So we have reached the point now where we know how to make this matrix operate on vectors written in terms of the eigenbasis. All we have to do is just transform the vector written in terms of the eigenbasis back to the standard basis first, right? And so to have this matrix 16, 42, -7, -19 operate on this vector 5, -4 written in terms of the eigenbasis. All we have to do is pre-multiply this thing by the matrix that sends it back to the standard basis. Okay? So we have 16, 42, -7, -19. We're going to pre-multiply by this transformation here. We've already seen this product here just amounts to -7, 1. And now we've got that same vector but written in terms of the standard basis. And then we just multiply, right? 16 and 7 is what? 70 plus 42, so -112. Let me see if I did this in the notes so we can avoid some of the arithmetic. Looks like I did not do this in the notes. All right, so we're doing it by hand then. Plus 42, and then we're going to get 49, and -19. And so what do we get? -70, is that right?
Yep.
And 30. All right, we did it. Hardest problem all day. All right, so any questions on, and this is written in terms of the standard basis. Any questions on what we've done so far? So hopefully this feels a little bit funny because, how often do you really want to take a vector written in terms of one basis, perform a transformation on it, and then leave it in terms of another basis? Kind of, hopefully that feels a little bit funny. Isn't it natural to sort of want to always stay in terms of the same basis to where when you operate it on it in one basis, you can re-express the answer in terms of that same basis? The answer is obvious, right? And so what are we supposed to do if our current procedure transforms into the standard basis and just leaves us there? The answer is, of course, just change it back, right? So to get our answer back into terms of the eigenbasis, what we'll do is transform it back using the inverse of -3, -2, 1, 1. Okay. All right, so what we've done so far is we've currently operated on a vector that was in terms of the eigenbasis by transforming it back into the standard coordinates and then transforming using that matrix that was written in terms of the standard basis. And now what we're going to do is we've got this inverse matrix that will send vectors that are currently in terms of the standard basis back into terms of the eigenbasis. So that inverse then is going to undo the process of converting from eigenbasis to standard. It'll undo that and send us from the standard back to the eigenbasis. So if you recall, we had this vector -7, -70, 30 that had resulted from inputting a vector in terms of the eigenbasis through that transformation. And so this is currently written in terms of the standard basis. And so what we'll do then is let's operate on it with this inverse matrix. And that will then send us back to the eigenbasis. So here's the vector that resulted from that transformation of the standard basis. We just multiply all this stuff out. We get 70 minus 60, which is 10. -70 plus 90, which is 20. So this is now the result of that transformation written in terms of the eigenbasis. And what we've done so far has been piecemeal, where we had a vector in terms of the eigenbasis, transformed it to the standard basis, and then operated on it with the transformation. Then we took that result and undid that coordinate transformation to get us back in terms of the eigenbasis. But usually, of course, we do it all at once. So to do it all at once, what we do is we would take we have our vector written in terms of the eigenbasis, transform it to the standard, operate on it with this matrix written in terms of the standard coordinates, and then transform back. And what we do is we do this all at once. So we basically treat this thing as a single linear transformation. And so what we can do is we can just multiply all this stuff out, right? So matrix multiplication we know is associative, so it doesn't matter what order that you multiply these things in. So you can just start multiplying from left to right. If you multiply this one by this, you'd end up with this matrix here. So multiply those first two matrices, you'd get -2, -4, -5, -15. And you can multiply this matrix. Multiplying those matrices ends up giving you 2, 0, 0, -5 times this vector written in terms of the eigenbasis. And from here, it's just a matrix operating on a vector. You just multiply this out, you'd end up getting 2 times 5 is 10. -5 times -4 gives you +20. And so this transformation then took a vector in the eigenbasis and returned another vector, also written in terms of the eigenbasis. And so the sort of end of the story, the sort of point of this whole thing is that this transformation, 2, 0, 0, negative 5, is the same transformation as what we saw before. This one, however, is written in terms of the standard basis. And this has the same exact geometry. We're just using a different basis to describe the matrix. And in this setup, the geometry of this transformation is painfully clear. It takes 2 to the first eigenvector, and it takes negative 5 to the second eigenvector, and just rescales them according to that. So that is sort of the wonder and the importance of change of basis in determining the structure of a linear transformation.